So I'd like to start this with talking about why L'Hopital's rule came about. And we're going to look at a couple limits that we've already seen and see why we would need something like this. So the first one I want to look at is a limit that you should know, but maybe you don't. You may not remember it, maybe you do. And it's a limit as theta approaches 0 of sine of theta over theta. When we saw this limit for the first time, we ran into a problem. Anybody remember what the problem was? Or can you figure out what the problem is? It's 0 over 0, right? So on top, sine of 0 is 0. And on the bottom, we get theta is 0. So we get 0 over 0. And this 0 over 0 is what's called an indeterminate form. In your previous math classes, you've learned a couple of rules. The first rule being 0 divided by anything is 0. But anything divided by 0 is undefined. So we have two conflicting rules here. We have one rule saying the answer should be 0, another rule saying that the answer should be undefined, or actually now our calculus knowledge would say anything divided by 0 is infinite, right? Might be positive infinity, might be negative infinity, but it would be infinite. At least if we're dealing with numbers around 0. And remember, if we're doing a limit, we're not dealing with theta equals 0, we're dealing with theta close to 0. So we have one rule saying it should be 0, one rule saying that it should be infinite. Well, those are conflicting, right? And so what we did was we looked at a picture, and we plugged numbers in. We looked at the data, and we said, okay, if theta is 0.1, what's going to happen? If theta is 0.01, what's going to happen? And we looked at what happens as it gets closer and closer. Does anybody remember what this limit equals?
1.
Yes, it does equal 1. Good. So the limit of sine of theta over theta as theta approaches 0 is equal to 1. We looked at it graphically. We looked at it using a table of data. What we're going to do now is we're going to be able to look at this analytically also. And we'll come back to it when the time is right. Here's another one that we did early in the year, at least this type of problem. And this one was not as big a problem. We were actually able to evaluate this analytically, but we had to go through quite a bit of work to do it. So what we did here, and we came up with some rules to avoid some of this work, but what we did is we said that this is equal to the limit as n approaches infinity of, and then we divided each term by n squared. So we ended up with 3 plus 1 over n squared over 6 plus 5 over n. And then we said since n is going to infinity, then we know that these terms here, where n is in the denominator, those are going to go to what?
0.
Those will go to 0, and so what we end up with is 3 over 6, or 1/2. And we came up with a rule and said, in this type of limit, as n approaches infinity, we can just divide the leading coefficients as long as the degree on the top and the bottom are the same, right? Well, what L'Hopital's rule is going to do for us is deal with these types of limits in a way that's a lot easier without having to come up with rules like that. We can generalize it, and it makes things a lot easier for us.